Good afternoon, everyone. I'm Cassie with AABC, and I'd like to welcome you to today's Tab Talk webinar. I also want to thank our sponsor, IMI Hydronic Engineering, for supporting this session. Just a few items to cover before we get started. Presenters will be holding questions until the end of the presentation, but we encourage you to submit them at any time using the Q&A button at the bottom of your screen. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists so that our producer, Will, can assist you. This presentation is being recorded and will be available for viewing in 1 week. In terms of continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their email within 24 hours. And finally, if you are a certified TBE or TBT, your CEUs for attending any webinar in this series will be automatically uploaded to your respective portal after the webinar. Today's webinar is Different Types of Hydronic Balancing and Their Impact on Controllability with Muslim Nazarali and Rafael Mordini. Muslim F. Nazarali, TBE, president of Air Technology Consulting LLC, is certified by several testing and balancing associations. He has been involved in the HVAC industry since 1986. He is a member of the Associated Air Balance Council and the National Environmental Balancing Bureau. Rafael Mordini is the lead engineer for the Engineering Support Center with IMI Hydronic North America. With over 10 years of experience in the industry, which includes 4 years as hydronic training manager for North America, Rafael collaborates closely with engineers on hydronic design projects in multiple countries. Currently, as an ESC team leader at IMI, Rafael is responsible for providing knowledge of various system and product solutions to clients, reviewing hydronic designs, and making recommendations for optimal performance. Without further ado, I'd like to hand it over to our presenters to kick us off.
Hello, good afternoon. Today we will talk about the different types of hydronic balancing and their impact on controllability in our HVAC wall. I'm going to have Rafael take over from here with further explanation.
Thank you, Muslim. So let's kick off our presentation here, okay? So again, today we'll be looking at different types of hydronic balancing and how they affect the controllability of the control valves. Moving on, we just remind us what is the objective of a HVAC system, right? We need to ensure the comfort in the rooms and doing this by consuming the lowest energy possible, right? That's what makes us engineer here, right? Also, just to explain why there's so much technology about this, is because 40% of the energy in the world has been used inside buildings. And within that, 50% is for HVAC systems. So we can roughly say 20% of the energy in the world is on HVAC. So any dollar that we save, any percentage that we save, might be a significant amount of dollars by the end of the year. And some buildings, they take more energy than others, like a hospital, take 5 to 7 times more energy than a regular office building. With that being said, let's talk about the hydronic system by itself. Why do we care about the flow rates of a particular terminal unit? Well, the cooling or heating power of your terminal unit is defined by the flow rate that is passing there and the delta T, the differential temperature between the supply and the return pipe. We need to ensure both of them in order to guarantee a good cooling or heating output from the terminal unit. We need both of them, and they're in the same formula. If you change one, the other will be affected. That's why we say that the flow rate can be the cause and the delta be the consequence. The delta T can be the consequence. We'll see better on the next slide. So let's take a look on this example here. We have a coil that's designed for 10 GPM, supply temperature 180 degrees, with a delta T of 40 degrees, so the return temperature is 140. Well, what if we're unbalancing the system? What if we have 15 GPM? In this case, what happens is that the water, that drop of water that goes inside that enter on the coil will be faster now because of the flow rate is higher. It means that this water will spend less time inside the coil and will leave the coil without being able to exchange all its heat. And that's why now the return temperature increased from 140 to 160 degrees. And this can be worse as we increase even more the flow rates. In this case here, 20 GPM. So the delta T now is just 10. The return temperature is 170. It's because the water is so fast there inside, there's not enough time to exchange its heat. So this water now will come back to the mechanical room, to the boiler room, in a higher temperature that should be. And how will this affect our system? Let's take this example here with the chiller. The chillers, they have their coefficient of operation, the COP. And we can see on this chart, let me bring my laser here, laser point. Okay, perfect. We can take a look on how the COP goes down as we decrease the return temperature. So if you have a return temperature of 54.5 degrees, we will keep the COP of 5. But if we increase the flow rate on the system and start to see too much water going in some coils that they don't have enough time to change its heat, the return temperature will be affected and will start to be colder and colder and colder. See this example here. If the return temperature in this chiller is 51.8, the COP will be 4.2. What does that mean? It means that now the chiller is taking more electrical energy in order to cool down the same water to the same supply temperature. It's not being as efficient as before. Okay, we can see here that we can lose 15% of the COP pretty easily just because the system is not balanced. Okay, this is significant because the chiller is the equipment in the system that takes more energy from the system, right? Is the biggest consumer there. Moving on, talking about a unbalanced system. Ashley bring to us from the HVAC applications handbook this curve here. That's pretty much the coil curve. It shows the flow rate by the heat output, but could be cooling output as well. See that this here is not linear, okay? This here shows to us that for let's say this is our design output for that room, we might need 100% of the flow. This is the design flow rate that we aim when we're balancing the system. If for some reason the system is unbalanced and we have the double of the flow rate, this happens, right? Take a look on the picture on the left. We have our boiler room here on the bottom, okay, on the underground, and we have this riser that's attending all those consumers. Notice that the first ones, it's too hot for them. They're sweating. And the other ones that are far away from the pump, they're freezing. Why? Because probably the first ones, they have overflow. And the other ones, not that much. Okay? Some people might think, but the control system, the BMS, will notice the overflow. And this is incorrect. Okay? We are not measuring flow rate in the system. The only thing we measure is the temperature in the room. But take a look on the coil when we double the flow rate there. So we should have 100% of flow, but now we have 200. Take a look on the heat output, 200% of flow rate. So 100% of excess of flow rates there give us just an extra 6% of heating output. What does that mean? It means that your system is practically blind for this unbalanced situation. Or for sure, your system will know that the last units here, they are starving. There's no flow rate for them. But what can they do besides open more their control valves? Nothing, right? The system is not smart like that, oh, close the first valves in the system so we bring water to the last ones. Unfortunately, that's not how the BMS works. So 6% of extra heating, it takes some time until the system, the thermostat in the room to feel that we have is too hot, you know, and we have to start to close the control valves and push the excess of water to the other floors. That's the main issue. Here we'll see some explanation why the system got imbalanced. Okay, so here we have our pump, could be our primary or secondary pump, the one that takes care of the terminal units, our circuits, and you see that the first ones, they're too red, means that they're receiving too much flow rate, and the other ones, they're too cold. This happens because of differential pressure. What is the differential pressure? It's the dynamic pressure that we have on the system. This pump here will provide this to us. The pump creates pressure. The pump is not there to give us flow rate. The flow rate is a consequence of the available pressure that we have. Imagine all the circuits here, they are identicals, same apartments, everything is equal. But why do we get different flow rates? Because the available pressure that's achieving each of them is not the same, because the water is losing pressure by friction on the internal walls of the pipe, on the supply pipe and also on the return. So it's easier to the water to go to the first equipment and go back. If you compare with the last one, the water has to run much more piping and go back. So the available pressure can be shown on this chart here. It's big for the first equipment, and as we start to go further and further on the system, the available pressure will decrease and decrease and decrease. This is how we can identify the index circuit, the most critical one, right? You just have to find out the one with the lowest differential pressure. In this case here, this poor guy doesn't have enough. In some cases, in some projects, you go to measure the flow rate and it has zero flow rate. It looks like your pump is not even on, you know, but the pump is on, it's at 60 Hertz, right? The first equipments can tell. So how do we fix that? What can we do? Well, the easiest solution that was created back in the 50s was balancing valves. The balancing valves can fix that. How? Well, the balancing valve will give the same differential pressure to all terminal units. How? Well, if you have excess of available pressure here, we create some pressure drop on the bottom of this valve. This valve will be responsible to absorb any excess. And now they all will receive the same available pressure. And if they are identical, they will receive the same flow rate as well. And everybody's happy here. No one is sweating and no one is freezing cold. Let's keep moving. Here, some math behind the balancing. Let's take a look on this example. We have here our primary pump that takes care of the chiller room. For this example, we don't care about what we have on the chiller room. We have here the decoupling bypass, right? And the secondary pump. This one is what matters to us. And this pump is responsible to give pressure for us to make the water flow through all those identical 4 circuits. We have some pressure drops here. So in between the circuits, we have one pressure drop on the supply pipe and an extra one on the return pipe between them. We also have 1 foot of pressure drop on the piping here on the circuit, 4 pressure drop on the circuit, on the coil of the fan coil unit, and 5 for the control valve. So let's calculate how much pressure we need from this pump here in order to make the water flow through just the first equipment. So there's no pressure drop here, as I can see. I have 1 from the pipe, so plus 4 from the coil, it's 5 already, and 1 from the control valve is 10. Here's a magical pipe. There's no pressure drop here. And we deliver the water to the suction of the next pump. So the total available pressure that is needed for the first equipment, it's 10. Well, but let's take a look on the second one. Will the second one take the same 10? Well, the second one takes the same 10 because they are equal, but also one from the supply and one from this return, a total 12. And we can do the same thing with the third one that will increase to 14 and the fourth one that goes to 16. It means that the pump that we size will be a 16 head pump. So this pump, in fact, is oversized for the other equipments. And they will steal the water. The water is lazy, guys. When the water gets to this T connection, the water has to decide, am I flowing through and going to the next equipment, or I will try to fit on the first equipment here? It's easier to go on this one, right? So they will try to fit here, increasing the flow rate until it's too difficult. No more water can get here. And then goes to the next one. So our goal here is to install the balancing valves. You see them here on the return. This is one picture of could be any balancing valve. So as we are adding balancing valves, we are adding something on the system. Every single valve or accessories, they represent a pressure drop for the system. So let's consider for the fan coil number 4 here, the circuit 4, this valve here will create 1 foot of pressure drop for us. Why 1 foot? It usually is what the delta P meters need to have a valid measurement for flow rates, right? So let's consider 1 foot. So the total here now for this circuit number 4 is 17. This is our pump. The pump here takes 17. Will be sized for 17 feet of head. So our goal on the balancing here is to make all the circuits take the same 17. They will be all equal to the pump. How can I do that? Well, just look at the formulas. We are missing something there. That it's going to be the pressure drops that will be added on the balancing valves. Okay, here it is. Notice that as we get closer to the pump, the pressure drop increase. It means that this valve here will have to create more pressure drop because there's more excess of available pressure. Okay, this is the math behind the balancing. I know that when we are in the job site, we are not doing these calculations. We don't know how much pressure drop we'll have in a segment of pipe, right? Doesn't make sense. We have our own methods to figure out, but this here is just the math behind it. If I know some people try to balancing on their design, which is almost impossible, right? So let's talk about the first type of balancing valve that can fix that, can be used on there. There's the manual balancing valves, okay? The manual balancing valves, we have mostly 3 different designs. We have the globe style here, multi-turn. You have like 4, 5, or 10 turns on this hand wheel. We have the very popular circuit setter. They're smaller, they're easier to work with, but the adjustment is smaller. You don't have many turns here. It's usually just 1 turn on the hand wheel. And we have the Venturis one here, right? When you have a Venturi here, that gives you a good quality of measurement when you're adjusting the ball valve here. So these 3 valves, they work like the same. They're static balancing valves. And when we're using these valves, this is a symbol of a balancing valve. You see the PD ports here and the hand wheel, the gray valve. When you're using this, we can create modules on our system by using a partner valve. This is a regular balancing valve, but for a whole module, like this here is a module. Could be a floor on the building, could be a whole riser, or just a small branch on a floor. You can create a module with that. And then you have some benefits like the proportional rule. What is the proportional rule? It says that when you have any disturbance in pressure upstream, all the equipments downstream, they will be affected the same way. So how can I use that? Well, we can use this for easier balancing. It means that if I decrease here like 10 GPM, they will be equally distributed here. All of them, they will lose the same percentage of flow rate, you know. This makes the balancing faster because, you know, a big system could be a hell because you adjust one valve and then you go to the next one, you go to the next one and the next one. When you finish, you go back to the first one and the flow rate's not the same anymore, right? Because the valves, they interact between themselves. So you can use this here to do some, like to do the balancing, the rough parts, and you do the fine balancing on the terminal units here using these balancing valves. And also when you create modules like this, you can use pump optimization because our goal here, guys, on the balancing is not just achieve the design flow rate, right? Because we have to optimize the pump. The pump that is installed there is always oversized. It's oversized because the engineers, the mechanical contractor, he has to ensure that the pump that's installed will be enough for the system. They can't risk to install a pump and during the tab, they find out that they are 10% short in pumping, you know? So this pump here is always oversized. And I'm from Brazil. And here in Brazil, the consultant engineer, the designers, they put some safety factory there, you know, on the pump. And the mechanical contractor, when they're installing it, they put their own safety factor. So by the end of the day, we have a huge pump there. And if you just close these valves and get the design flow rate, are you saving the energy that much? You know, what you should do is try to balancing between them and trying to figure out the overflow that you might have on this branch. And you use this valve here to remove this overflow. So let's say this here is a small branch and a floor. Then you do this on the entire floor. And then you do this balancing within all the floors on a riser. And then we are going to balancing the risers. In a certain moment, we'll have a main valve there that will be passing the flow rate of the entire pump. You don't have to close this valve. In fact, sometimes this valve not even exist on the system, right? You just finally were able to identify how much overflow you have on your pump because now the entire system has like 15, 20% of overflow. And then you decrease the pump rotation. You go on the VFD, you start to decrease. The pump doesn't need to be running at 60 hertz. You find out that you just need 55, 54. And then you create your set point. And that's how you do a perfect balancing. You save the energy there doing your balancing. Okay. Well, now the system is all balanced. As you can see, we have my 4 terminal units, all of them with 10 GPM. Let's put these control valves to work. Let's simulate some low load situations. So I will close one of them. I close the control valve on the terminal 1. I don't know, maybe the person who is on this off-C here is not there at the moment, so you just close the valve. There's no need for air conditioning here, so you close it. Notice what happened with the neighbor valves here. They all get more flow rate, 13, 13, 13. Is the interactivity that we saw when we were first doing our balancing. The same thing happened when a control valve closes. The system doesn't care if you're closing a balancing valve or a control valve, something closed, and this is going to affect the neighbor valves. Can the balancing valve fix that? No, it can't. So let's close more. Terminal 3 closed halfway down. We were expecting 5 GPM, but in fact, we have 8. We have overflow at this moment. And what happened with the neighbors? Oh, even more, 15 GPM. No good. And if you close the number 2, this here that we were expecting 5 GPM, we even have 11, more than the design flow rate for that equipment. And the terminal 4 here has 17. So this is a big issue that we have on HVAC systems. And this happens because of how the available pressure varies. We already saw these charts today, right? So if here's the pump, as we go inside the system, we are losing pressure on the supply. Here is a circuit and we lose pressure on the return. And here we can see how much pressure the pump is giving to us. But at low load conditions, the flow rate on the pipes decrease, right? Because we are not at 100% of the flow rate there. If the flow rate on the pipes decrease, their pressure drop decreases as well. This is the main issue. The resistance that we have on these pipes, they almost disappear. So now more pressure goes to the to the terminal units. And the ones that are more far away from the pump, they are more affected. You see this huge gap here in both sides compared with the small gap here in the beginning. So the ones that are more far away from the pump, they're more affected. We have the delta P sensor that try to fix that, but as the curves change here, you still have some overflow on the first equipment. Okay, this is no cool. Here's some, this scheme here show us how we try to control the flow rate in a terminal unit. Okay, so we have our valve here, the K4, and we have the coil here on the K5. They're connected by the flow rate. The flow rate that passes on the valve is the same flow rate through the coil. Well, we already saw this curve here today. It was one of my first slides. It shows the flow rate by the cooling or heating transfer in a coil. This is pretty much standard. It can vary a little bit, but it's pretty much that. So for proportional control, modulating control, what we do, we create a control valve that's a mirror from the terminal units. You see how they are the opposite? Because on this way, when one plus the other will give us this global characteristics that's linear. This is how the BMS thinks, guys. So the BMS thinks that if you're sending 6 volts, so 60% of the opening on the valve, you want 60% of cooling. It's linear like that. Okay. In this case here, the slide is showing 50%. We can take a look on our curves here. So we need 50% of cooling or heating power. It means that we just need 20% of the flow rate. So I will develop a control valve that with 20% of control of flow rate, I have the valve open at 50%, you know? One compensates the other. In this way, we have this linearity here. That's our goal. But at low load conditions, this here will be deformed, unfortunately. The control valve that originally has this curve here will have its curve deformed. And this happens because of variation of pressure. Okay. This happens when the valve is closing on its circuit. You know, your whole system is full open and you decide to close just one valve. When you close this valve, you're close like 50%, 20%, you already start to deform its curve. And also in a big picture, like when you have a whole system, just because you close one valve here, the available pressure in the neighbor valve increases and you start to deform this curve a little bit. What ASHRAE says about it? Well, ASHRAE has a chart here that shows the authority of the control valve. That's how they call it. If you have an authority of 1, you preserve a perfect curve here. But as the pressure increases over the control valve, this here can be deformed more and more. ASHRAE says that the minimum acceptable is 0.25. They say that for design conditions should be 0.5, and for minimum critical situations in the system should be 0.25. I'm not going through the math on this here, how we determine the authority. This is another subject, but just so you know, guys, that if you have authority worse than 0.25, that's this green line here, your controllability is no good at all. And this is not caused by the balancing valves, okay? This is just caused because of the interactivity that we have on the system. And the balancing valve that we have there is a static balancing valve. The name says it's static. It can't do anything anymore for us. We just adjust it during the balancing phase for design conditions. After that, the valve is just a fancy accessory there, right? So anything worse than this green line here It should be better to have an on-off control valve there. You're just wasting your money on controllability. You can find control valves hunting position, opening and closing, never find the position to stop, you know. So now let's take a look at another technology for balancing valves. We have the automatic balancing valve. It's also very popular in America. Okay, let's take a look how it works. Those valves, usually they have a cartridge like that inside the valve. You see it, you have several types of cartridges here. Each manufacturer, they have their own collection of cartridges. These here are the ones that I could find. And these cartridges, you have some pressure ranges that this cartridge can work. The most popular in our market, there are two ranges, like the low range that's from 2 to 32 psi, and the other one that's from 5 to 60 psi. And they give us a good accuracy on flow rates, around 5%, which is pretty good. How it works? We pretty much have a piston here attached to a spring, and you see on the side of the piston, we have some apertures where the water can flow through. You see here, the water go through here. And this here changes, so as the pressure in the system changes. So if a neighbor valve closed, the pressure increases here. So this here can take action, compress the spring a little bit, and keep the flow constant to us. It's a good technology. Let's take a look on the same example again, but now considering autoflow valves. So I will close the first terminal circuit, go to zero. Notice that the neighbors didn't feel it at all. On the previously slide, on the previous solution, we saw 13 GPM here, and now it's just 10. So we solved that. No overflow, right? Let's see. So we closed the terminal 3. We closed it halfway, we were expecting 5 GPM. But we don't have 5 GPM, we have 8. What happened? We'll see. Then we close the second one, 0, and here we keep 8 GPM. Okay. What happens is this, guys. When we have the automatic flow control valve working with a modulating control valve, the curve can be deformed as well. The same thing that before. But this curve looks worse, right? It may happen. Imagine that you have a automatic flow control valve installed in a circuit very far away from the pump. You barely has excess of available pressure. So you're here on the beginning of this chart. You have 2 psi of available of pressure drop on this valve. This valve is barely working. The spring is full extended, the piston here, right? So if the control valve decides to close just a little bit, like 10%, this valve here will have less than 2 psi of pressure drop, so we won't be working anymore. We'll be out of the range. So that's why if you're in the position 5 here on this chart, you see that the curve is still awesome here. You have the perfect EQM curve. The authority is 1. So you can control your modulating with no issues. But as we start to look at the other terminal units that we may have closer to the pump, you will notice that the available pressure across the pressure drop across the valve increases, right? It's easy. We have the 2 PT ports on an automatic flow control valve. You just measure there. Let's say that you have 20 psi, right? So 20 psi would be something around this 0.3 here. It means that this spring here is halfway down compressed, and now the area of passage of the water decreased, the CV of the valve changed, so the flow rate keeps the same, right? But look at this. This is going to be the control curve for the control valve here. Imagine that we want just 10% less heating on that room. So you send 9 volts, right? 9 volts would be 90%, would be something like that. As you send 9 volts, the control valve closes a little bit. And what happened? Well, the spring here will extend a little bit as well. The two valves, they will be working against each other until this here will be full extended. And this gets worse and worse as we get closer to the pump or closer to this edge of this range here, 32 psi, right? Look at this case, the case 1, when you're almost full compressed. You're closing a lot the control valve and nothing's changing on the flow rate because the automatic flow control valve is compensating. I would say that these curves here, 2 and 1, they're definitely worse than authority 0.25. This here doesn't work for modulating control at all. We should be using on off here. Oh, but I really need modulating control. Well, unfortunately, in this case, we should be sizing better your control valves. That's not the subject here, right? We're just telling you that the balancing valves, they can't help you on that. Sometimes we have this false assumption that one balancing valve can fix controllability, which can't, you know? But there's one valve that helps us here. That's the peak V's. The actuator is very white, right? It's like a camouflage on the background. But here's an actuator, okay, guys? So you see this valve here is a control valve. They're very popular nowadays in our market. It's a peak V. How it works? Well, it's a control valve, as you can tell by the actuator, and it has here the hand wheel. It's inside the actuator. You have to remove it in this module here to access the hand wheel. We have PT ports, so you can measure to do the balancing, and you see this belly part here. This here is what ensure a good controllability on the control valve. Let's take a better look. Again, the same example, how the flow rates react when we close the valve. So closing terminal 1, nothing changed, like the automatic flow balancing valves, right? But let's close halfway down terminal 3. Oh, now we got the 5 GPM that we need. It means that the controllability of this valve is good, it's preserved. Let's close terminal 2. Nothing happened on the others. You see? So that's why we have this name, pressure independent control valve, because all circuits now are independent from each other. And also the controllability is preserved. How it works? Well, take a look on this. It looks like we have two, in this example, in this valve, we have two seats on the valve. We have here, you see the control plug, so the actuator is here. And the actuator go take this steam up and down and closing the valve here. So here is the seat of the control plug. And here's another seat, but this is for the delta P control part, that belly part there, right? This here keeps moving like a automatic flow balancing valve. It keeps moving, keeping something constant, but differently. The balancing valve, this here is keeping delta P across the seat constant instead of the flow constant. This is very different. Take a look here on this drawing. It shows to us. It's like we have two valves, one right after the other. When you're measuring this valve here, you're measuring P2 to P3. If your valve is measuring from this purple here to this blue here, you are measuring across the seat of the valve and you can measure the true flow across the valve. So makes the balancing much easier. But pay attention, some manufacturers, this red PD port is connected to this P1 pressure. And in this case, you can't measure the flow. It's going to be like automatic flow balancing device because this part here keeps moving like the cartridge from the previous valve. This here keeps moving, so we don't know what's the total CV here for us to do the math. So if a peak V has this PD port here on P1, unfortunately, you can't measure the flow rate. You just can't see if you're outside the range and trust that you have the correct flow rate, which I believe it is the correct one. But if this PD port here is connected to the P21, now you're measuring just across the seats of the control valve, and this CV we know, and this here, this is how we can figure out exactly what's the flow rate that's passing there. And how do I adjust this valve? Usually those valves, they have a hand wheel. This one is here. You see the handle, X in this case here looks like it's 0 or bubble tight shut off. and we have the position from 10 to 1. Some manufacturers, they imprint here already the flow rate, so you know, you just point this arrow here to the flow rate that you want. Some manufacturers, you will need a table to tell you like the position 10 gives you that many GPM, and the position 8 gives you that much GPM. Okay, this is how they work. Okay, you still are able to do balancing on this valve, but those are control valves that in fact do balancing for us. Okay, is there any control valve by itself that can do the balancing? Some people think that the BMS can take over of the balancing, which is not true. The BMS is there to vary the capacity of the terminal unit, right? There's just one valve that's a new technology that's out there nowadays that can do the balancing by itself. That's some smart valves like Belimo Energy Valve or IMI TA Smart. Those valves, they have flow sensors installed inside them. Ultrasonic or magnetic sensors, doesn't matter. What matters is they are measuring the flow rates, and they know when they overflow at any circumstance. Oh, I am halfway closed. I should have just 20% of the flow rate, but I have 30. Okay, the valve does its own correction. But that's the only way for you to have a control system to balancing the system for you. If you don't have those smart valves with flow sensors, you still need balancing. It could be a static balancing valve, it could be a automatic flow balancing valve, or you can have the balancing integrated on the control valves like PICVs. Okay, guys? I think this is the end of the presentation that I prepared for you today. Let's go ahead and see if you have any questions.
All right, thank you so much for that presentation. It was very enlightening, and we appreciate you doing this webinar today. We don't have any questions coming in at the moment, but I have a couple of our sample questions prepared. So we can start with those and then see if those prompt anybody to submit some questions. So the first one is, what are the recommendations for the installation of the balancing valves?
The recommendation for balancing valves that we see, usually we are measuring those valves, right? So we need to ensure that we have a good quality of measurement. Usually we have a recommendation of 5D 2D. It means that 5 diameters of straight pipe before the inlet of the valve and 2 diameters on the outlet of the valve. In this way, we remove some turbulence on the water, and we have a steady measurement on the PT ports using our delta P meter, okay? And there's also a common practice to install balancing valves on the return pipe. Usually because we have more space there, because the strainer is on the supply, and also because some people decide, so I don't want to create pressure drop before the coil, just to avoid as the pressure goes down to some bubbles to show up or things like that. So it's more common to find the balancing valves on the return pipe as well. Okay.
All right, the next, okay, we've got one coming in through the Q&A. It says, why do you call them auto-flow valves when actually they only flow limiters and cannot automatically increase flow?
Yeah, because there's some markets call it like that. In my market here in Brazil, we call as flow limiting devices. Okay, that is just how some markets call them. Okay.
All right, next we have, how does the use of variable flow pumping and the placement of the DP sensor controlling pump flow affect the valve selection or types of valves?
That's a good question, because for sure we need to have a VFD to save energy in low load conditions, and we will have a delta P sensor installed somewhere to tell the pump when to slow down, right? For the balancing valves, doesn't affect anything at all. because the balancing will be selected and designed for the design situation in the system. And what is the design situation? It's the worst case scenario. Is when all the circuits are requesting full load. So it's when your pump is running at 60 hertz and you need 100% of flow rate in all of the circuits, unless you as engineer, you decide that you have some, I hate this word because of my accent, simultaneously. It's when you say that you don't need 100% of your entire building. Let's say you have two risers and you say, oh, in the morning, this riser here takes more water, but in the afternoon, it's going to be this one that takes more water. And then you do some math and you find out that in fact, you don't need 100% of flow rate at any time. The maximum that you need is 80%. In this case, yes, you have to balance your valve still for the design conditions, but the balancing process will be different because as you won't have enough flow rates to balance the entire system at once, usually you close one riser, balancing the second one, and then vice versa until you get the whole thing balanced, and you let your delta P sensor and the VFT to run and ensure that those 80% that you need for your system. Okay.
All right, thank you. This next question says, through the presentation, you arrived at better and better solutions, but I'm assuming the cost goes up. Do you have any advice for dealing with systems with the limitations you noted earlier in the presentation?
Yes, for sure. Valves that has more engineering involved, they will for sure cost more. But take a look on the PIC-V, for example. It's not just the balancing valve that's going to be replaced by that one. The control valve as well. So it's pretty much you're taking the control valve and the balancing valve, integrating them in one valve. It's not fair to compare the price of a static or out-of-flow valve and compare to a PIC-V. It's not fair because there's more thing on that, more other things on that math. That would be the control valve as well. Also the connections, because now it's easier to install, right? And the labor as well. So, but I can tell you for sure, by the end of the day, it's going to be a little bit more expensive. But you would be surprised at how cheap the PIC-Vs are getting nowadays, as they are becoming more and more popular. Okay.
All right, thank you. This one says, what is the maximum number of balancing valves you recommend before you have a branch valve, and do you recommend a branch valve for each floor on a multi-floor building?
Yeah, that's a good question because usually we want to avoid that fish spine project. You know, when you have a main pipe and all of the balancing valves, they're hanging from that main pipe, right? The balancing starts to become a nightmare. Even though nowadays we have some good methods to do that, sometimes when I receive projects here in my department and we give suggestions. Sometimes we say, oh, you have too many valves here. Why don't you break up in some small branches and run them in parallel here? And you decrease by like 12, 15 valves maximum per branch. There's not a fixed number for that. It depends of how much available pressure you have reaching that branch, and what is the difference in available pressure when you compare the first equipment to be attended and the last one. Because we want to avoid the situation that you find a balancing valve that you have to close so much the handle to absorb the excess of available pressure that you're pretty much closed. You notice, like, if you take one of those multi-turn valves, even though the valve has 10 turns, you have to absorb like 40, 50 feet of head. You will be dealing with a final adjustment of less than half turn or one turn. It starts to get difficult, and the accuracy on your hand to change that is a small degree on the handle will already vary too much the flow rate. So unfortunately, the answer that I will give to you, it depends. If you have like a data center that all the equipments are pretty much the same, the pipe, the distribution pipe between them is pretty much oversized, so you don't have much pressure drop between the equipments. In this case, you can have dozens of them in the same loop, and the balancing will still be easy. But if you have a big branch where the first one is receiving too much more pressure if compared to the last one, and the balancing becomes a nightmare as well. So it depends, unfortunately. Okay.
All right. This says, what % energy savings have you seen by balancing HVAC systems?
Yes, we even have a number here in the company that we use to promote. When you do a proper balancing and you're saving energy from the pump by optimizing it, you can save easily up to 30% of pumping energy. Okay, it's not the total HVAC energy, but from the pump you can save up to 30%. Okay, because the pumps are oversized. If you just run your system, you're not saving much thing, right? If you just go there and close the valves until you get the design flow rates, you save a little bit because now the pump is pumping less water, but still not enough. If you're able to find out how much oversized your pump is, you can save up to 30%. Okay, and for the peak V solution, as the valve is adapting itself by in low load conditions, you can save up to 40%. You gain extra 10% on that.
All right, thank you. Everyone, we have about 5 more minutes for the Q&A session, so if you have other questions, please submit them now. Our next sample question is, can I balance my system just by using the control system?
Yeah, I pretty much answered that on during the presentation, but the answer is no. The control valves are there to control partial loads in the system. It's unfair with the control valve to make the valve like, let's say we are in a room that has too much flow rates. The control valve is going to react for sure, but it's unfair with its controllability if you will never find this valve 100% open. Let's say that the system is so unbalanced that this control valve is never more than 50% open. It means that now I just have from 0 to 5 volts, thinking in a modulating control valve, right? So 0 to 5 volts to control the flow rate. And now we killed half of its controllability just because we are trying, we didn't balance, and the control system is trying to do this for us. Okay, it's not its job, and that's why balancing valves are much important for the standard control valves. Okay.
All right, and then how important is it to optimize the pump?
Oh, very important, right? I mentioned that everybody puts some, as I say, some fat on the pump, just some safety factor there. And sometimes we are sizing the pump thinking in future expansions. And this expansion might take 4 or 5 years, you know? So if you don't optimize your pump, we'll be wasting a ton of energy during the year. It's very important.
All right, those are all the questions I have at the moment. Is there anything else that you would like to share with the group before we close out?
No, just to say thank you guys for your attention, for being on this webinar.
Awesome.
Now I want to add to that. I think as a balance engineer, I would really recommend the engineers and the owners to have these circuit setters and auto flows in the system from the balanceability and the energy standpoint.
All right, thank you for that. Just make sure we've got all the Q&A questions answered. Someone asked about the automatic balancing valve being used for temperature change. Can you address that?
I don't think I understand the question. Being used for temperature change, like a changeover? If it's for changeover, unfortunately, the valve can only deal with one flow rate, right? Because the cooling flow rate will be different than the heating one. And then you will have overflow in one of the cases. If you're using changeover, my guess to you is you can use one automatic flow device in each supply or return. So you ensure that the flow rate that's going to the coil will be the right one, or you can use a peak V on the common supply or return after the 6-way control valve. Okay. Because the peak V can adjust itself through the actuator for different flow rates.
All right, thank you so much. That is a wrap for today's webinar. Thank you, Muslim and Rafael, for a great presentation and discussion. And thank you again to IMI Hydronic Engineering for sponsoring this webinar. Last but not least, I want to thank everyone for joining us today. Before we wrap up, I want to remind you all that registration is open for the AABC annual meeting, which will be happening October 9th through 11th in Lost Pines, Texas. Be sure to visit aabc.com to register. And thank you so much for your valuable time attending this webinar, and we will see you at the next one.